We've been talking about working with tensors. And in particular, I've been telling you that everything you know about vectors and matrices is subsumed within this tensor notation, right? It all can be written in a single unified way in terms of this tensor notation. And so one of the things that we've talked about is how to make a dot product. And so a dot product is a way to combine two vectors to make a scalar. And so we could say v dot u is vx ux plus vy uy plus v z u.
John, it doesn't look like whatever you're doing is getting, whatever you're writing is getting added to the whiteboard.
It's not.
It's not. It just says new homework posted on Blackboard due November 9th.
That is so weird because it's showing up on my laptop screen. It's getting transferred over. All right, let's see if I can debug this. Huh. Well, that's frustrating, isn't it? Okay, well, clearly that's not working. Okay, as an emergency measure, I will go back to my old iPad and connect it with a cable. All right, sorry about that. Break my heart. So I'll try to figure out a different way to get it to work. All right, let me stop the sharing. Okay, and I'll connect the old one. There's always something. Okay, so let's try again. Share with a cable. Share. All right, you see something that looks like an iPad, right? Okay, and then if I go to Good Notes, and do I have today's one? No, I don't. Oh, well, create. Okay, let's go back to the beginning. What am I doing, right? So I'm showing you that everything with tensors, that everything with vectors and matrices works in this tensor notation, right? And so one of the things is a dot product. You can read this now, correct? Good. Okay, so that is a v dot u. And that can be written nicely in this tensor notation as vi ui, which is automatically summed over I equals 1, 2, or 3. So this is v1 or vx ux plus vy uy plus vz uz. And another example that I showed you is a cross product. So a v cross u, right? This is a way to combine two vectors to make another vector. And so if we say w is v cross u, then the ith component of w is the Levi-Civita symbol sub ijk, vj, uk. All right, now, those are two ways to multiply vectors. There's a third way. That is what I will show you now. The third way is maybe less well known than the other two, but it's also very useful. It's called a tensor product. And so this is a way to combine two vectors to make a tensor. And so we could do that to say the tensor T is V tensor product U, like that. And what this means in components is just T I J is V I U J. Right? So in this equation that I just wrote, there are two free indices, right? So this equation is true for I equals X and Y and Z, and J equals X and Y and Z. So this equation is 9 equations in one. Okay? So this equation means that Txx is Vx Ux, and Txy is Vx Uy, etc. Right? There are 9 such equations. Or if I want to write it out in an array, we could say that Tij is Vx Ux, Vx Uy, Vx Uz, Vy Ux, etc. Okay, so this is a third way of multiplying matrices, or excuse me, of multiplying vectors. And so, you know, there are 3 different kinds of products, and they produce different sorts of output. Right? So they produce the output of a scalar and a vector and a tensor. And in particular, a tensor of rank 2.
Excuse me. Is there a simple way to visualize this tensor product in terms of V and U?
I was going to ask the same question, like how the cross product is, it's really easy to visualize because it's a vector perpendicular to the other two.
Great question. I don't have a great answer. I'm going to be talking more about visualization in the next class, and so maybe I'll see if I can think of a good answer for you by then. Yeah, let me ponder that one, and I'll get back to you. Thanks. Although I don't have a visualization, I do have a little bit of vocabulary. Okay, so there are other words that you might hear for these things. And so a dot product is also known as an inner product. These words mean the same thing. Okay, dot product and inner product. A tensor product is also known as an outer product. And it is also known as a dyad. Okay. And the people who call it a dyad use a slightly different notation. They sometimes will write this as VU with nothing in between the vectors, just VU. Okay, and so when it's written like that, with nothing in between the vectors, then it normally means a dyad, that is to say, an outer product, unless you're Russian. Russian people tend to write an inner product, a dot product, as two vectors with nothing in between them. And so you just have to figure out by context if the person means that sort of thing, right? You could, for example, look at the names of the author and see if the author is Russian. Or better yet, you could look at what else is in the equation and see whether the thing that belongs at that place in the equation ought to be a scalar or a tensor. Okay, so this is another way of doing the multiplication. Okay, so this is a concept that you might or might not have seen before, and it certainly fits into this tensor notation. It is, it's the easiest thing in the world to write in terms of tensor notation, just like that. Okay, let's tell you another example. Okay, how about for derivatives of vector fields? So when you studied multivariable calculus, you learned about ways to take derivatives, right? And you have learned in particular about three operations called the gradient, the divergence, and the curl. Right, and I trust these things are familiar to you. I mean, this is a part of multivariable calculus, right, that goes into liquid crystal science. You know that these things are all based on the gradient operator, right? And so there's an operator like this, which means d by dx in the x component, and d by dy in the y place, and d by dz in the z component. Okay. A shorter way of writing those derivatives is to write d sub x. So just the partial derivative sub x, partial derivative sub y, partial derivative sub z. Right? So these symbols mean the same thing as that. Okay, partial sub x means partial by partial x, partial sub y means partial by partial y, partial sub z means partial by partial z. Okay, now you can apply this to a scalar. Right? So we could, here, I'll make more room. We could apply it to a scalar. Some f of x, y, and z. And if we apply it to a scalar, you get a vector, right? The grad f, which means partial f, partial x, partial f, partial y, partial f, partial z. Okay, so this is taking the three derivatives of any function f and putting them into a vector. Or in this more compact notation that I'm showing you, we could write it as grad xf, grad yf, grad zf, like that. Now we can make things even more compact by using our tensor component notation, right? We could say if there is some vector, right? If we want this to be a vector W, okay, then W sub I is the derivative with respect to coordinate I of F. Okay? So this equation means the same thing as this vector expression. All right, so this is saying for all I, the ith component of W is the derivative of F with respect to coordinate I. So this works really nicely for the gradient of a scalar field. Okay? We can do the same sort of thing for the divergence of a vector field. So for the divergence of a vector field, you know that there's a scalar, which is del dot, whoops, not F, del dot V. Okay, so this is del x vx plus del y vy plus del z vz. Or it could be written nice and compactly as del I vi, because you remember the index I here is repeated exactly twice in this expression. And so we automatically are summing over, we are contracting over the index I. So this is a scalar, right? This is scalar S. Then the third derivative operator that you are accustomed to is the curl of a vector field. And so that could be written as del cross V, and this makes some vector U. And this is a lot of work to write out, right? We have to say del y v z minus del z vy, and the same thing in the other two positions. Okay? When we use our component notation, we can write this nice and compactly as u sub I is epsilon I jk del j v k. So this is the same notation as a cross product, right? And as we have a cross right there, right? So the cross means we're combining the indices in this way with the Levi-Civita symbol out in front. So this quantity is automatically contracted over the indices j and k, where I remains as a free index. So the right side of this expression is the sum of 9 terms, but luckily most of the terms are 0. We only have 2 non-zero terms. Okay, so this is a nice way that we can make this notation pretty compact and include all these concepts about vector derivatives. Okay? So recognizing that this V is a vector field, right? This thing, it's a vector field a v as a function of x, y, and z. And then in an expression here, right, this derivative acts on the vector field. Right? And so it takes the derivative of the vector field with respect to coordinate number j. So coordinate number j is x or y or z. There's another notation that is even more compact that I want to mention it to you, even though I don't personally use it. And I just want to mention it to you so that if you ever see it, you'll know what people are talking about. Okay. And the more compact notation is to write symbols with a comma. Okay. To write vi comma j to mean the derivative with respect to coordinate j of vi. Okay. So that means that the thing after the comma is instructions to differentiate with respect to this coordinate. With respect to coordinate j. You'll see this in articles sometimes. Especially engineers use this kind of notation. I don't know why, it's just a cultural thing in some communities. And there could even be more things before or after the comma, right? And so if you have a T, I, J, comma, K, L, that means the derivative with respect to coordinate K, the derivative with respect to coordinate L of T, I, J, right? Because the K and the L are after the comma. And so you're differentiating with respect to those things. But the I and the J are before the comma. And so you're not differentiating with respect to those. And then you still follow the same rules about repeated indices, right? And so V I comma I means del I V I, which means the divergence of V. Right? So this is the super compact way of writing the divergence. And if you're differentiating scalars, you don't even need anything in front of the comma. Right? So you could write a scalar f sub comma I. All right, and that means, it looks funny, but it means d by di twice, acting on f. Right? So that means the second derivative of f with respect to x plus the second derivative of f with respect to y plus the second derivative of f with respect to z. Or in other words, the Laplacian of f. Okay, so I don't personally use this, but you might see it someday, and if you ever do, you can remember me. Okay. So that is yet another notation. Okay. What else can we do in this notation? All right, well, we could do the trace of a matrix. So you remember from when you were studying matrices, if you have a 3 by 3, right, with some mx x plus my plus m, not plus, mxx, myy, mzz, and then there could be anything here, mxy, et cetera, okay? Then the trace of the matrix, written as TR of M, is defined as the sum of the things on the diagonal. So mxx plus myy plus mzz, independent of all of the other terms that are off of the diagonal. So the things off the diagonal might be 0, they might be not 0, it doesn't matter. The trace is the sum of the things on the diagonal. There. This is another thing that is extremely easy to write in terms of this tensor component notation. We just write m sub I, right? Because here the index I is repeated exactly twice. So you automatically sum over it. So mxx plus myy plus mzz. All right, so that is quite easy to write in terms of this notation. There's a related thing that you probably have seen in linear algebra classes, which is a little bit more of a pain to write in this notation, and that's the determinant. Okay. So the determinant of a matrix, okay, so as you may remember, you get the determinant by multiplying in different ways and adding or subtracting the terms, right? And so you take the product here, whoops, here, right? Plus here, plus here. You add up those things and then you subtract this, minus this, minus this times this, right? Is that familiar to some of you, right? You've seen that in math classes, right? It is possible to write this in this component notation that I am showing you, but it is surprisingly complicated compared to everything else. It's something which depends on the dimensionality, and I'll show you how to do it in 3 dimensions. Okay, in 3 dimensions, whoops, in 3 dimensions, there is weird identity, which you could prove if you really want to, that the determinant of a matrix is 1/6 of the trace of the matrix cubed minus 1/2 the trace of matrix squared times the trace of the matrix plus 1/3 of the trace of the matrix cubed, right? So the matrix cubed means m times m times m, right? Matrix multiplication. Okay, so this is a true but kind of weird identity that you can work out in detail. And then if you express each of these things in excruciating detail, that is 1/6 of MII J, J, M, K, K, minus 1/2 M, I, J, M, J, I, M, K, K, plus 1/3 M, I, J, M, J, K, M, K, I. Yeah, this is not a really commonly used thing in expression in tensor operations, but it's good to know that it exists in case you ever need it. Okay, so this is a good pausing point. Are there any questions about any of these things? No.
We have a matrix which is the tensor product of U and V. Can we express the determinant of this matrix in terms of the length of U and V?
I'm sure you can express it in terms of the length of U and the length of V and the dot product, U dot V, right? Because the determinant is a scalar, right? And it must be related to the other scalars that you can form. I bet you could do that for practice. Why don't you do it for practice and show me? Yes, that'll be great. Let me just point out one thing to you about the notation here, right? So just to show you an example, right here, I wrote the trace of M, and it's the trace of M to the third power. Okay, so to write that out, I had to write out the trace of M times the trace of M times the trace of M. Okay, so look, MII, that's the trace of M. MJJ, that's the trace of M. MKK, that's the trace of M. Okay, so this is MII, MJJ, MKK, that's a trace of M, quantity cubed. Okay. You'll notice the first time I wrote it, I put the index I 2 times. The second time I wrote it, I put the index J 2 times. The third time I wrote it, I put the index K 2 times. Okay. I did not recycle the index I, right? I did not say MII times MII, right? Because if I did that, I'd be using the index I 4 times, right? And that would violate rule number 3. Right? Or if I did it in all these places, I'd be using the index I 6 times. That would really violate rule number 3. Okay. And then if somebody came along, they wouldn't really know how to interpret the thing that I wrote down. And they would probably interpret it wrong and get something which depends on the trace of coordinate system. Okay. So this is the way to avoid problems like that. It's you use a different letter each time you need one. Right? And so I needed a letter here, I picked I. I needed a letter here, I picked J. I needed a letter here, and I picked K, to make 3 separate dummy indices. Okay, so this is meant to prove to you what maybe you didn't need to have proved to you, that everything in terms of vectors and matrices you can write in this very nice notation. Now, I'd like to move on to a couple of other things to tell you about tensors. I was planning to now talk about what happens to tensors when you do different kinds of operations. Like what happens if you rotate coordinate systems? That is, if you start with this coordinate system and you change to this or this, right? How do all the components change? I'm running a little behind schedule, and so I am going to skip talking about that in the classes, although it is written up in the text, and please do take a look at that. Okay, so for transformation under rotation, please see section 9.4. I'm going to skip that for now. And I want to go on to a different kind of transformation. That is transformation under inversion. And so this is from section 9.5. This is an interesting point, which does turn out to be quite relevant to liquid crystal science. So let me spend a little time talking about this. There are a couple ways to present this subject. Okay? Let me first present it in, well, what's my favorite way? I don't know if it's anybody else's favorite. Okay. You know that I don't want anything to depend on arbitrary choices, right? I want to say that the laws of physics are independent of any arbitrary choices that we might make, right? So the laws of physics don't depend on a choice of units, right? There's some nice international treaty that establishes the SI unit system, but nature doesn't care about international treaties, right? So it doesn't matter what units we use. Right? Similarly, it doesn't matter what coordinate system we use, right? We could have a Cartesian coordinate system like this and rotate it to anything else, and the laws of physics should stay the same. There's one other arbitrary choice that we need to be careful about. Okay, and that is the arbitrary choice of the right-hand rule. We use the right-hand rule when we define cross products. Right? That is, we say, if we take the cross product of one vector cross another one, then we use the right hand, and the thumb marks the direction to go in. Right? You might ask, what's so great about the right hand? Why not the left hand? Why don't we use the left hand rule instead to define the cross product of vectors? In that case, it would be the cross product from there to there, go down, right? If we use the left hand rule, we would get the negative of what we get from using the right hand rule. So this is another arbitrary choice that we have to watch out for. Now, I showed you how to do cross products in terms of the Levi-Civita symbol. Okay. So as you recall, the Levi-Civita symbol, epsilon ijk, is defined as +1 if I, j, and k are x, y, z, or y, z, x, or z, x, y, and defined to be -1 if I, j, k are z, y, x, or y, x, z, or x, z, y, and 0 otherwise. This symbol has the same arbitrariness as the right-hand rule versus the left-hand rule, right? So basically, the right-hand rule goes into the choice of which of these things is +1 and which of those things is -1. If we were to switch from the right-hand rule to the left-hand rule, then we would have a different definition of epsilon, right? So with the left-hand rule, epsilon ijk would be -1 if if ijk is x, y, z, etc. +1 if ijk is zx, zyx, etc., or 0 otherwise. Okay. Nobody actually uses this thing, right? It's like an international treaty, sort of, to use the right-hand rule. Okay, so don't actually learn this. Don't learn that thing, but we could, in principle, use that. So how do we avoid the arbitrariness when we choose sign? The answer to that is that we need to categorize tensor expressions depending on whether they involve that arbitrary choice or not. Okay, so categorize tensor expressions. Well, and not just tensor expressions, but scalar and vector and tensor expressions based on whether they depend on the sign of epsilon ijk. And that means whether they depend on the right-hand rule versus the left-hand rule. So that means there are some expressions with 0 powers of epsilon ijk, right? They don't have any epsilons in there, right? Or 2 powers, or 4 powers, right? Or any even number of powers, right? Those things don't depend on whether you have the right-hand rule or the left-hand rule. On the other hand, there are expressions with 1 power of epsilon ijk, or 3 powers, or any number, any odd number of powers, an odd number of powers. These are different kinds of expressions because they do depend on the choice of the right-hand rule versus the left-hand rule. So we can still use them, but we have to watch out for them and be careful about how we work with them. Okay, So in order to use them, we need names for these things. Okay, so these things are called a proper vector or a proper scalar or a proper tensor. These are called a pseudo vector or a pseudo scalar or a pseudo tensor. Another old-fashioned word that you might come across sometimes, this is called a polar vector versus an axial vector. That's an old-fashioned terminology that I don't especially like myself, but it's out there in the literature. Okay, so let me show you some examples because I think all this becomes clearer with examples. Okay. So let's think about some common vectors in physics, like the position vector, r, or the momentum vector, p. These things are proper vectors. They don't have anything to do with the right-hand rule, right? There's no epsilon, there's no right-hand rule that's involved in them, right? On the other hand, if you look at the angular momentum, you remember from classical mechanics, angular momentum is defined as r cross p, okay? There's a cross product there. There's one cross product. There's an odd number of cross products there. Okay? That makes it a pseudo vector. For another example, the force is a proper vector, but the torque, tau, is r cross f. That is a pseudo vector. Okay, what else do we have? Well, let's think about electromagnetism, right? The electric field, that has nothing to do with cross products. That's a proper vector. By comparison, the magnetic field, B, this is defined with cross products, right? For example, if we have a solenoid with a current running around, right? Then we say, let's use the right hand to go in the current direction, and then the thumb makes the magnetic field. So there is one power of the right-hand rule there. So the magnetic field is a pseudo vector. So just as a check, one equation that you might remember from electricity and magnetism is for the force, the force on a moving point charge. Right, the Lorentz force is F is the charge Q times E plus V cross B. Okay, so let's check all the expressions here. Okay. The force is a proper vector. The electric field is a proper vector. V is a proper vector. The magnetic field is a pseudo vector. Okay. Now, when we look at this combination, a proper vector cross a pseudo vector. Okay. So there is one power of epsilon, one power of pseudoness, right? That is for this B. There's another power that is this cross product out in front. Okay. So this combination V cross B is a proper vector. So we have E, that's one proper vector, plus V cross B is another proper vector. So this whole thing is a proper vector, times Q is a scalar, and that gives us a proper vector. Okay. So this equation is great. Okay. So the thing to notice is that all equations have to be the same kind of object on both sides, right? They can be proper vector equals proper vector, or pseudo vector equals pseudo vector, or no, proper scalar equals proper scalar, or pseudo scalar equals pseudo scalar. Right? But you'll never have an equation that says proper vector equals a pseudo vector, right? Or proper vector equals pseudo vector. No, you can't do this, right? Or proper scalar equals pseudo scalar. You can't do that either, right? Because the equation might be true in with one choice of the right-hand rule, but it wouldn't be true if you choose the left-hand rule, right? Because one side of the equation would change sign and the other one wouldn't, right? But as long as you have proper equals proper or pseudo equals pseudo, no problem. Right? If it's proper equals proper, if you switch which hand you use, everything stays the same. If it's pseudo equals pseudo, and you switch which hand you use, everything changes sign. Either way, you're okay, right? It's only if you were to mix them, if you try to set, proper equals pseudo, that would make trouble, right? Or if you ever wrote an equation that involved electric field plus magnetic field, that would make trouble, right? Because when you change right-hand rule to left-hand rule, one of those would change sign and the other one would not. So those are things not to do. And in that way, you will avoid the arbitrariness of the right-hand rule or the left-hand rule. Okay, I'm going to stop talking here. In the next class, I'll say a little bit more about inversion and then talk about visualization of tensors. And I'll see if I can come up with a good answer to the question that Cheng stumped me with earlier. Okay, I'll stop here. Thank you, guys.